Hi everyone, today we are performing another acoustic optimization example with Nastran Solution 200. This example is a little different from the one I just did. This example uses a built-in beta method functionality inside of MSc Nastran. So this is what we plan on doing. We are going to do essentially the same thing as before. We have this acoustic box that I believe is on this slide. What we are going to do is we are going to try and minimize the pressure distribution as much as possible for the given force and frequency range. You can see here in orange is our starting pressure distribution, but here in blue is what the optimizer is able to do towards the end. So now, where do you find this example? This example can be found in the Nastran Optimization's User's Guide, Chapter 8. The example is called Acoustic Optimization. Basically, we have a fluid cavity enclosed by a structural mesh. We are going to be varying some of the dimensions of the thicknesses so we can minimize the acoustic pressure, if you will. Here's just a snapshot of the optimization problem statement. Like I said, we are going to be varying the thicknesses of the various structural strips. Before, in the other method of using the beta method, we had to manually create the beta design variable. This variable is automatically generated in this example, and I'll show you how it's automatically generated. Our objective is going to be the following. Although we won't have to explicitly define an equation for this, Nastran will automatically create this objective equation for us. So I'll explain more in a moment. Let's go ahead and see here. And comment regarding the constraints. For the constraints, we won't have to manually type out this equation constraint. And Nastran has an internal beta method. We can just program one objective and it will automatically create both this objective equation and this second equation constraint. And then third, we are going to create a weight constraint. We want to preserve the weight as much as possible. So now let's go ahead and talk about how to obtain this initial term. You're going to need this term from the previous example. So here, let's go ahead and get that term right now. So here's the set of files from my previous example. If we look here, I believe it's here. If not, I might have to get it from a second run. Here it is. So this is the starting objective, if you will, from the starting constraint value from the last example. You're going to need this value to do this example. So now, once you know where that value came from, let's go ahead and talk about some other additional support. If you're a professional engineer, if you want guidance, if you want information, if you want training on how to perform acoustic optimization, you can contact me at this email address and I will get back to you with an answer. If you are a student or engineer and you want access to the Nastran Solution 200 web app, you can also contact me at this email address and I will work on getting you that access. Let's go ahead and start this tutorial. You're going to need the starting file. The starting file can be found inside of the tutorial section. If you scroll down, there'll be a section called Acoustic Optimization Beta. Right click on the file and save the file to your desktop. So this is the file we're starting off with. This file was produced by my pre-post processor that you see here. Basically, this file contains the entire acoustic box. So here's that. Now to start off with, go back to the web app, click on the size link. This is going to load the size optimization web app. Import the PDF file and upload it. I hope you've seen my previous tutorial on this. I hope you know that once you click these plus icons, you can automatically generate the design variables. Here, I believe the range of design variables were, let me look at my notes, 0.00 and 1. So here, 0.001 and 1. We'll go ahead and click this and we'll automatically select all these plus icons. You can see I've accidentally set the Young's modulus, the Poisson ratio, and the density as design variables. So here I'll just go ahead and delete those 3 design variables. I'll also remove design variable x3. We are not modifying the thickness for P shell 3, so we can just delete that. And here, let's make sure we've given upper bounds to all of these. So once that is complete, we can move on to the objective. Here, we need to use, in order to use this built-in beta method, we need to switch to the equation objective. Here, to start off with, we'll go ahead and say that we are focusing on the pressure. We are focusing on the first component of pressure, and this is for node 11280. Let me make sure I typed in 2 there. So this is going to represent each pressure point for this entire graph, if you will. That's what A1 is representing. It's representing every point in this graph. Now let's go back up here and type in A1. Here, let me just look at my notes and make sure this is properly set. Right, so here I'll go ahead and type in A1. If you click on the options and mark the checkbox for functions C1, C2, C3, this is what's going to enable you to use the beta method. Once you have the beta method, you have to supply C2 and C3. Alternatively, you can leave the boxes blank, but usually you want to use the normalized constraint value from your previous acoustic optimization attempt. So here, let's go ahead and show that again. And what I want to do here is select this value. So here I'm leaving out the rest of the notation since this is the same as E00. Here I'll go ahead and paste this value here, 1.047198. And for C3, by default the value is 10 if you leave it blank. But here, this problem behaves better if you type in a value of 5. Now let's see, what else do I need to do here? I think that's essentially it. Remember, this is a big contrast to before. Before I had to create all of these different expressions and so on and so on. Here with just this one row, Nastran will automatically define this objective equation. It will automatically generate this equation constraint too. And this is because we are using this beta method. So now what else do I have to do? If I go to settings, let's go ahead and update some of these settings. I'm going to change the convergence tolerance and the maximum constraint value. Here the convergence value will be 0.081 and the maximum constraint value will now be 0.015. So this value is going to help the optimizer finish sooner. This works for this example. This is problem dependent, so there's no guarantee it works on every example. I've just done this example so many times that I know it helps. Here, I'm going to say that we're going to be a little bit more relaxed regarding what we consider a constraint as being violated. So anything less than 0.015 will be satisfied. And now let's see what else. I need to change the approximation method to direct linearization. Let's go ahead and move to the exporter. We'll download this new package. And here, this is the second zip file. So I'll go ahead and rename this beta method. And then simply double click this desktop icon to start the optimization. This example takes a few moments. Here you can see the status page is going to go and run this through design cycle 1, 2, 3, 4 until the very end. So we'll go ahead and let this work by itself. And I'll go ahead and start talking about the results. So let me see if the results are here. Remember that we want to take this pressure distribution across all the forcing frequencies, and we want to minimize that. If you look at the last version of this example I did, we had to create all of these different objective equations and constraint equations. What's different about this example, I generated one equation objective, and Nastran internally will automatically generate all of those additional equations for me. Here's just a glimpse of what the expected solution should look like in blue. Let's go ahead and go back to the web app and see where it's at. So here, let me see. I can tell that we've successfully performed the optimization. Here I get a message, run terminated due to hard convergence. Here we see that the objective value started at a value of 1 and it went down to a value of 0.139. And here you see that the normalized constraints, we have a few that are taking part in the constraint value, but here after that, the constraints are no longer taking part. This happens because the optimizer sees that none of the constraints are being violated, so they are removed since they're not impacting the optimization as much. Here you can see the change in design variables, and here let me go ahead and look at x1. So here, the thickness for design variable x1 started at a value of 0.02493, and at the end it ended at a value of 0.0035909. So one last comment before we look at the new pressure or acoustic pressure from this optimized model. If we look at the design variables again, you see that there's a design variable beta. If we look back in the web app, there is no beta design variable in this list. So here I have x1 through x7. When we specify this objective equation using the beta method, with C2 and C3 defined, Nastran internally generates the beta design variable. It automatically creates the objective and equation constraint. All we had to do to define the constraint was simply the weight constraint. So I believe that is actually one thing I forgot here. I did. So I did forget to include the weight as a constraint. We'll go ahead and do that now actually. That explains why that optimization went through really quickly. So 2890 and 2910. And then once we do that, we'll go ahead and go back to the exporter and we'll go ahead and repeat this process. So here what happened again is I forgot to include the weight as a constraint. So that was an error on my part. We'll go ahead and correct that and perform this optimization again. So it would be worth showing you how less complicated this example is compared to the previous tutorial. So here on the left is the common method of performing this beta method for acoustic optimization. If you look at the problem statement, you can see that we had to manually define this equation objective. Then we had to manually define this equation constraint expression. But here in this example, we didn't have to create all of these additional things. We just had to define one line here in the web app, again using the beta method and the C2 and C3 terms. And right now the optimization is still going through, so I think I'll pause the video here and just wait for it to conclude. So the optimization is complete. Let's go ahead and look at the results now. You can see that the objective went from a value of 1 and it ended at a value of 0.019553. Let's go ahead and see what happened to our design variables. Everything looks good. Our normalized constraints, you can see we have some constraints are being violated. That's why they're positive, 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 positive. And then towards the end, you should start having numbers that are really, really close to values of 4. Here you'll notice that towards the end, we have a value of 0.0085496. So this value is dependent on the Gmax value here. So 0.015. And now let's go ahead and look at the results in our preprocessor. So here, this pressure distribution is from the initial design with the starting design variables for the thicknesses. What is the new pressure distribution look like? So let me go ahead and delete the old results. Let me go ahead and attach the new results. In the folder, where we perform this beta method, there's a new result file. This result file contains both the initial pressure results and the optimized pressure results. So here, if you look at the results here, you'll see that a set of the data has D0. D0 stands for the initial design. So if we look here at the horizontal axis labels, initial can be considered the 0 design cycle. And then here we should find results for the 24th design cycle. So if we look back here and we scroll down, you see we start having results for D24 or the 24th design cycle. So here what I can do now, I can select all of these pressure values for all of those forcing frequencies. I can select pressure here, select node 11280. Let's see, I want to append this. Appending means you're going to plot on the same curve that you see here. We're going to use the logarithmic scale. Let's make sure we're using the magnitude for the complex number, and we'll click apply. And here you can see that this original red pressure distribution has actually been minimized, as you can see here in the new blue curve. And that was the intent of this tutorial. We wanted to minimize the acoustic pressure for this. So the last thing we want to do, this PDF file that we started off with has old data for the thicknesses. So here we have 0.02493. If we look back at the web app and we look at just the X1 term, you can see that we started off with 0.02493, but we ended at 0.001. So how do we update these values? If you look in the directory where the optimization was performed, there is a PCH file. This PCH file has updated values for the thicknesses. So here for thickness 1, it's 0.001, which matches the value 0.001 here. You'll notice that in the same PCH file, we also have the thicknesses for the other ones, P shell 4, 5, 6, and 7. So what I can do now, I can move this file to the right, and I can copy these P shells and move them to the right. So first, let's delete P shells 4 through 7, and we will delete P shells 1 through 2. And in here, we'll paste P shells 1, 2, 4, 5, 6, and 7. You notice that now this file has all the new thicknesses. Close the other files. And then I'll save this file as a new version. So this new file that I'm creating, called updated, has the new thicknesses. So here on my desktop is the new file. The file on the right is updated with the new thicknesses, and the file on the right, or the left rather, has my old thicknesses. And that was the last thing I wanted to show you in this tutorial, the process of updating your structural model with the optimized thicknesses. That's the end of this tutorial. Again, if you are an engineer and you have questions regarding this example, if you have questions regarding your own example, you can reach me at this email address at the bottom of the screen. If you're a student or engineer and you want access to the web app, I can also grant you access to that. Simply send me an email with your request and I will get back to you. With that, I'll close it there and thank you for watching.